All right, so this module and lecture will discuss lactate threshold, which is another kind of like keyword buzz term in the exercise physiology world. So lactase dehydrogenase is an enzyme that catalyzes the conversion of pyruvic acid to lactic acid. So you all have seen the schematic on the right several times now. And so this is really the area that we are talking about is this conversion and this catalyst of pyruvate to lactic acid. So this action is also reversible, which as you can see from the arrows here, that shows that it is reversible from pyruvic acid to lactic acid to pyruvic acid. So slow muscle fibers contain lactase dehydrogenase that promote the conversion of lactic acid to pyruvic acid. So when you begin a graded exercise test, like we talked about in our VO2 max lecture, you are probably recruiting slow muscle fibers. However, as the exercise intensity increases, so slow muscle fibers are going to be recruited when you first kind of get into that light, easy jog. So as the exercise intensity increases, this involves more fast twitch fibers. So LDH is found in greater concentration in fast twitch fibers. So this enzyme is found in greater concentration in fast twitch fibers. So defining the lactate threshold, when we talk about the onset of blood lactic acid or OBLA, this is lactic acid that appears in the blood when oxygen delivery is insufficient to support our normal metabolic demands. So let's go ahead and we are going to draw a simplified, but a graph here. So let's go ahead on the x-axis, let's put percent of our VO2 max. So if we're working in a percent down here, we know that we're probably going to be at 100, 75. Oh gosh, this won't be to scale, but you'll get the idea. So our x-axis is percent VO2 max, and our y-axis is going to be our blood lactate. We'll just leave it at that. We'll keep it simple. So let's go ahead and have in red, let's have an untrained, young, healthy, but untrained individual. And then let's in the blue have a trained individual. So let's go ahead and first start with our untrained individual. So we're going to start down here with light exercise. And we're going to kind of go along with our untrained individual until about 50% of our VO2 max. And this is going to be moderate exercise. And then as we hit that 50%, we're going to increase pretty dramatically to 100% of our VO2 max, which will be heavy exercise. So then let's go ahead and take a look at our trained individual. So we're going to start here again with light exercise. And we're going to stay pretty steady and pretty easy until about 75% of VO2 max, where we'll then have kind of this sharp increase. And so whenever we see this lactate start to increase and we see the onset of blood lactic acid accumulation, that's the point at which you can't clear lactic acid as fast as you accumulate it. So that's around 50% for our untrained individual and around 75% of VO2 max for our trained individual. So here's another way to look at this same information that I just shared with you. So our lactic threshold, so this is going to be where lactate first appears. And then our onset of blood lactic acid accumulation, this is going to be when you can't clear that lactate. So for healthy but untrained persons, blood lactate begins to accumulate and rise in an exponential manner at about 50 to 55% of the maximal capacity for aerobic metabolism. However, in a trained individual, this will shift from about 65 to 80%. And again, it's variable because we're all different. So it's always good to have ranges and give ranges for these sort of things. So you can have, I'm going to write this out here. Lactate, we could have metabolic acidosis or metabolic acidosis. And so this is how much aerobic energy production you need to do a certain workload. So the more fit you are, the more you can have the aerobic system take over. The less fit you are, the less trained you are, the anaerobic system will take over. And we know that the anaerobic system means without oxygen, which means you are going to be converting that pyruvic acid into lactic acid instead of going down to acetyl-CoA on into the Krebs cycle and the electron transport chain. So let's look at lactate threshold in different types of runners. So this will be a pretty simplified graph here. We're going to have 3 colors. Let's have red be a sprinter. Let's have blue be like a mid distance, that 800 to 1500 meter runner. And then let's have pink be marathon. So if we look again to orient ourselves on this graph, we have speed on our x-axis, meters per second. Let's say about 3 to 3.5 meters per second is about 8 miles per hour. And then 6 miles per hour, let's say 6 meters per minute is about 13 miles per hour. I think that's right. So if we have a sprinter, let's go back to our red color here. A sprinter is going to have a lactate threshold occur so much sooner than if we had a mid-distance runner or a marathon runner. So again, just sort of a simplified graph to show typical lactate performance curves in 3 different types of runners. So the mechanisms to explain lactate threshold, exercise physiology, as we talked about way back in the beginning of class last week, that it's a new field, right? And so we are constantly learning, we are constantly gaining ways to understand new and use new technology. And so right now we're working in kind of the mechanistic realm to really understand and explain lactate threshold, because it's still kind of one of those mysteries as exercise physiologists and exercise scientists that we're just not quite sure why this happens. But there are some theories out there as to why we have that accumulation that leads to that like delayed onset muscle soreness, those sore muscles. So we'll talk about those now. So some of these are still being studied, but one of them is low muscle oxygen. The second is accelerated glycolysis. The third is going to be recruitment of fast twitch fibers. Which we know lactate dehydrogenase is in more concentrated amount in fast twitch fibers compared to slow. And then the fourth is going to be our reduced rate of lactate removal. So let's dive into a few of these mechanisms to finish up this lecture. So when we have low muscle oxygen, this means that we are in an anaerobic state, which means no oxygen. So is the rise in blood lactic acid during incremental exercise due to the lack of oxygen in the working muscle, or because of other reasons like the heart, the lung, the kidney, the brain, or the liver, for example, utilizing and taking up this oxygen. Another mechanism to explain the lactate threshold is accelerated glycolysis. So when NADH production exceeds transport, and what are they transporting? Electrons. So we know that NADH is our electron carrier. So when NADH production exceeds transport, we have failure to shuttle hydrogen ions. So this pyruvate to lactic acid formation is because of these unshuttled hydrogen ions, which could lead to this accelerated glycolysis. Another mechanism to explain the lactate threshold is this recruitment of fast twitch fibers. So we know that lactate dehydrogenase is found in a greater concentration in fast twitch fibers. So if you have an increase in exercise intensity, that means that you're going to have an increase in recruitment of fast twitch fibers. And that could be one of the reasons to explain the lactate threshold is the recruitment of these fast twitch fibers. So the practical use of the lactate threshold, your body is constantly producing lactate every second of the day, even at lower intensities, walking around casually. And your body can really kind of keep up with this removal. However, when exercise intensity increases, the lactate production increases, meaning more for your body to buffer and clear. So increase intensity means an increase in lactate production. And so your body is trying to buffer this effect, but your threshold is a level at which the balance starts to tip. So the level of lactate you're producing exceeds the amount your body is able to remove. This is why when you increase the intensity, you start to feel the effects of being fatigued and sore. So in exercise physiology and as exercise scientists, we talk about this idea behind lactate training. And it really is to try to increase your body's ability to efficiently handle lactate production. So essentially you're working at a higher intensity before production exceeds removal. So again, just with our graph, if we're at 50%, 100%, let's say, 80%, and we're untrained, whoa, that was supposed to be dashed, untrained versus trained, what we're trying to do is really move this lactate threshold so that we are that faster 100-meter runner, 200-meter runner, 300-meter runner. So training right below the lactate threshold is really where you need to be. So the Cori cycle, this is another idea around mechanisms to explain this lactate threshold. So the process of lactate shuttling enables glycogenolysis in one cell to supply the other cell with fuel for oxidation. So you remove lactate from the active muscles and then you use it to replenish glycogen restores from intense exercise. However, controversy does exist over the mechanisms that explain the sudden rise in lactate concentrations during incremental exercise. So how is lactate removed from the body? It's taken to the liver by the blood, and it's either oxidized to carbon dioxide and water, or it's converted to glucose, then glycogen, to be stored in the liver, and the muscles, so that it can later be restored. So the first one, it is either taken to the liver by the blood, and it's oxidized as either carbon dioxide and water, or it's converted to glucose and then glycogen to be stored in the liver and muscles to then later be used if needed. So we have discussed VO2 max and the VO2 max test. And so VO2 max by definition is the maximum or optimum rate at which your heart, lungs, and muscles can efficiently use oxygen. It is therefore often seen that if you improve a person's VO2 max, you will also improve the aerobic fitness level. After all, the more oxygen your body can take in and utilize, the more efficient you are going to be aerobically. So that concept makes sense. So in combining and sort of talking about VO2 max and lactate threshold, here you can see athlete 1 in red and athlete 2 in blue. And even though they have very similar running speeds and VO2 max, we can see that athlete 1 has a lactate threshold at about 70% of their VO2 max or their oxygen uptake, where athlete 2 is at about 60%. So really just that little bit more training right below that lactic threshold, which will get better and better over time. So that's where the overload principle comes in, of adapting and then doing more intensity and adapting and doing more intensity, so that you can edge out your competitor in the 800-meter runner or 1 mile by that half a second. So at what intensity do we usually see a rise in lactate? So this is generally in the 50 to 65% of VO2 max, and this is more in sort of the untrained individual. And so that can go up to about 75 or 80% in more elite endurance athletes. So around 60% intensity is really where you want to be working out. And we've talked about intensity quite a bit in this class, and we haven't actually determined intensity. And so we are going to put that into play for one of your homeworks. So stay tuned for that. But we use the Carbonin method to determine intensity and really what that means for your heart rate. So when we talk about intensity, we're talking about heart rate. So where should your heart rate be in order to produce the effect that you want? So we'll keep talking about this, but thanks for listening. See you on the next one.